Myself, Shripad Atkare from Sri Krishna Mahavidyalaya Gunjoti, affiliated to Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati, Sambhajinagar. My research topic is development of hexaferrite nanoparticles based on rare earth substitution for enhanced structural and magnetic properties under the guidance of Dr. Mahesh Kumar Mane, Associate Professor and Head Department of Physics, Shikshan Maharishi Guruvarya R.G. Shinde Mahavidyalaya Paranda. Topic of today's presentation is structural, magnetic and dielectric properties of high corrosive aluminum substituted strontium hexaferrite. So the outline of presentation includes introduction, experimental procedure, result and discussion, which contains structural analysis, spectral analysis, morphological properties, magnetic properties, dielectric properties, and conclusion. So we know that the M-type hexaferrite, which is the scientifically important material due to its unique properties and applications. The properties of the hexaferrite materials are depends upon the various factors such as method of synthesis, type of a dopant, amount of a dopant, value of a pH, sintering temperatures. So the substitution of strontium or Fe with the metal science makes the considerable changes in its structural, magnetic, dielectric as well as microabsorption properties. So therefore, the researchers are trying to enhance the properties of the strontium hexaferrite by adding the various metals ions. So in this point of view, in the present work, I have synthesized the aluminum substituted strontium hexaferrite by the Sol-Gel attocombustion method, which is sintered at the high temperature to examine the consequences on the structural, magnetic and dielectric properties of strontium hexaferrite due to the replacement of Fe by the aluminum ions. So as I have told, the material will be synthesized by the Sol-Gel attocombustion method. So here I have given the details about the Sol-Gel attocombustion method. So in the Sol-Gel attocombustion method, you know that all the precursors, that is the strontium nitrate, aluminum nitrate, ferric nitrate, and citric acids are dissolved, are taken in the stereochromatic amounts, are dissolved in the 200 ml of distilled water, and the solution was stirred to get the homogeneous solution. Once the homogeneous solution will be formed, the clockwise ammonia will be added to maintain the pH value to the 8, and after that the material will be heated at the 90 degrees Celsius with continuous stirring. After the several hours of heating and stirring, the solution will be converted into the aqueous gel, and at the end of the reaction the gel evaporates and the resultant products was obtained in the powder form. So the obtained powder will be sintered at the 1000 degrees Celsius in the muffle furnace for the 6 hours, and which will be sent for the further characterizations. So here the material will be characterized by the various characterization techniques such as XRD, FTIR, Raman, Efficient, EDAX, BATE, VSM, and dielectric measurement. So in the result and discussion, we can see the structural analysis. The material was firstly characterized by the XRD. So these are the XRD results. We can see all the XRD peaks are exactly matches with the standard data, and the most intense peak having the HKL values 114, that will give the confirmation of formation of single hexagonal structure as we compare these XRDs with the XRDs reported by the researchers in the previous literature. So here all the peaks exactly matches with the standard data, as well as the no secondary peaks, any other types of secondary peaks will be observed in this XRD. Okay, so this indicates the formation of a single hexagonal structure. The liquid refinements of the corresponding XRD is shown in this second figure. So from this liquid refinement, I have calculated the goodness factor, which is a chi-square, and its value is less than the 1.50. That indicates, that confirms the successful doping of aluminum into the strontium hexaferrite lattice. So from the XRD data, I have calculated the various factors such as the lattice parameters, C/A ratio, volume, crystallized size, X-ray density, as well as I have also calculated the lattice strain, microstrain, dislocation density, stacking fault. So from the data, firstly I have calculated the lattice parameters. Here we can see that the lattice parameters are found to be lattice parameters A and C. As the structure is hexagonal structure, it has the two lattice parameters A and C. So both the lattice parameters A and C found to be decreasing with increasing content of aluminum. So this type of a behavior is observed due to the difference in the ionic radii of the strontium and ferrium. Okay, sorry, due to the difference in the ionic radius of the aluminum and the ferrium. Okay, so this negative difference reduces the value of lattice parameters A and C. So these are the lattice parameters which was calculated from the liquid refinement, and both the have there is no so much difference between these two lattice parameters. Here we can easily observe that. After that, the value of C by A ratio remains constant for all concentrations. The volume of the material was found to be decreased with the increasing content of aluminum, as well as the crystallized size. We can see the crystallized size is less for the pure sample, and which was found to be larger for the sample containing the more concentration of aluminum. So we can say the crystallized size is goes on increasing with the increasing content of aluminum. Next factor is the X-ray density, which was found to be decreased with the aluminum content. So after that, here we can see the variation of crystallized size, lattice strain with the aluminum content, and the second figure indicates the variation of lattice strain and microstrain with the aluminum content. Here we can see the crystallized size is from the figure. We can conclude that the crystallized size goes on increasing as the aluminum content increases. Similarly, the lattice strain goes on decreasing with the increasing aluminum content. So this type of a behavior is observed because the lattice strain and crystallized size, both the factors are related to the full width half maxima. So crystallized size is directly related, or it directly depends upon the full width half maxima. So for the according to the corresponding XRD, I have calculated the full width half maxima, which was found to be increased. Therefore, crystallized size is also found to be increased. So in the case of lattice strain, the lattice strain is inversely depends upon the full width half maxima. So the lattice strain goes on decreasing due to the increment in the full width half maxima. So here the second figure indicates the decrement of the lattice strain and microstrain with the aluminum content. After that, the material will be characterized by the FTIR spectroscopy. So the successful synthesis of hexaferrite without presence of any secondary type of peaks, that we can say the impurity, we confirm the that we have confirmed by using this FTIR spectra. So it was done by observing the vibration peaks appearing in the FTIR spectroscopy. Here we can observe that the presence of vibration peaks between the 410 to 519 confirms the formation of hexagonal structure. So also it is observed that the peaks are found to be shifted towards the higher wave number. So this factor indicates the successful doping of aluminum into the strontium hexaferrite lattice. After that, the material will be characterized by the Raman spectroscopy. So this is the Raman spectra. So in this Raman spectra, the A1G, it is the Raman mode having the maximum intensity as compared to the other Raman modes. So here we can see this is the A1G modes, and it's according to the literature survey, its appearance between the 670 to 710 indicates the formation of a single hexagonal structure. So here we can see the most intense peak Raman mode, which is indexed at the 695. So this confirms the formation of a single hexagonal structure. Similar to the FTIR, we can observe that the Raman peaks are also shifted towards the higher wave number. After that, to study the morphological properties of the material will be characterized by the FESM. So in the FESM, we can say these are the FESM images. So in these images, we can see that the spherical, pyramidal, and irregular shape hexagonal platelet-like structure will be observed, which indicates the growth of grains in the various direction. The average particle size is examined by the FECM, and which was found to be appears larger than the crystallized size measured by the XRD line broadenings. So this discrepancy will observed due to the two factors. The first factor is the tendency of the crystal to clump together during the calcination, and the second is the and formation of agglomerates, and the polycrystalline nature of the magnetic material is the second factor. So according to due to these two factors, the crystallized size calculated from the FECM was found to be different than the crystallized size calculated by the XRD line broadening. So the particle size distribution in the form of histogram is shown in this figure for the concentration x is equals to 0.0, 0.6, and 1.0, which indicates the continuous and uniform distribution of the all the grains. So elemental composition, these are the EDAX spectra, in which indicates from which the elemental composition will be confirmed. All the EDAX spectra contains the presence of aluminum. So this indicates, and whose weight percent goes on increasing with increasing composition of the aluminum. That indicates the aluminum will be successfully get doped in the strontium hexaferrite lattice. After that, the material will be characterized by the bait, that is a nitrogen physisorption. So these are the graphs of this particular characterization, from which the surface area, pore size, volume will be calculated. So according to the bait equation, the bait surface area will be calculated, and this is shown in this table. Pore volume and average pore size in the nanometer will be calculated from this data, and all the results are indexed in this table. So after the morphological properties, the material will be characterized to study the magnetic properties of the material by the vibrating sample magnetometer. So the VSM data, here we can see the magnetic properties of the material will be shown in the form of a hysteresis loop. This is the magnetic behavior of the aluminum substituted strontium hexaferrite. Here we can see that the saturation magnetization goes on decreasing with increasing content of aluminum. Okay, this type of behavior will be observed due to the magnetic disturbance between the between the two lattices A and at the B sides. So the coercivity, okay, we can see the coercivity, the variation in the coercivity will be also observed. The maximum value of coercivity will be observed for the sample having the more value of having the more concentration of the aluminum. That is, for the last sample, the coercivity will be maximum. That can suggest that the material is aluminum substituted strontium hexaferrite is the good candidate for the permanent magnet applications. After that, the dielectric properties of the material will be studied by using the LCR meter, and these are the results. Dielectric, the first figure indicates the variation of dielectric constant with frequency, and tan delta versus the frequency. From this graph, we can see that as the frequency goes on increasing, dielectric constant was found to be decreased. Okay, the frequency goes on increasing and dielectric constant goes on decreasing. The reason behind is the super exchange interaction. Okay, the reason behind this, it is a space charge polarization. Due to the space charge polarization, when the frequency is more, then the dielectric constant is exhibit the external field, but as the frequency goes on increasing, it does not exhibit the external field, and this will alter the dielectric constant. Therefore, dielectric constant goes on decreasing as the frequency also increases. So these are the dielectric properties of the material. Similarly, in the second figure, we have seen the tan delta versus log F. As the frequency goes on increasing, tan delta also goes on decreasing. So lastly, in the conclusion, I have concluded by using this XRD FTIR, and Raman spectroscopy, the successful synthesis of strontium hexagonal ferrite with aluminum doping was verified. The signified changes in the spectral, morphological, magnetic, and dielectric properties were caused by the gradual shifts in the peak positions and modifications in the lattice parameters, which are attributed to the aluminum substitution. So the variations in the distribution of elements and gain shape that enable efficient aluminum doping into the ferrite lattice. Mesoporous structure have been detected using the nitrogen physics option studies, indicating the possible use in the variety of domain, and the material's strong corrosive properties suggest its permanent magnet applications are the good fit for the it. Okay, thank you.